Okay, then I think I'm going to introduce the first speaker, Pietro Altermatt. He's at Trina Solar. If you don't know Trina Solar, it's one of the biggest photovoltaic manufacturers in the world. I think last year they had number 2 in shipments of modules. But the top 3 are all very close. And he did his PhD at Constance. It's a really famous silicon photovoltaic center, one of the top in Europe for many years. And then he did research fellowship in Martin Green's group at UNSW, also, of course, super famous for silicon PV research. And more recently, he's become a professor, I think it's already more than 10 years now, at the University of Hanover, Leibniz University of Hanover, and is a principal scientist at Trina. So he has this mix of academia and industry, which is a really nice combination. And actually, I came first to know him at a conference, maybe it was 8 years ago or so in Germany, and he gave this plenary lecture where he was talking about all the things that you need to watch out for as an academic researcher to make sure that your research can be applicable in industrial PV. And in particular, at that time, was something that people forgot to do is that they would try to make some nanophotonic structure for anti-reflection coating, let's say, and they would forget that in a real module you have encapsulation in glass, and that totally changes the properties of that coating. And so you can have an amazing coating on silicon air, but then if you put it in a module, maybe it doesn't work as well as the industrial texture. And so he had a bunch of these little things like that, hey, just pay attention to this if you want to have more impact. Look out for it. And I think today he's also going to try to give us a little guide on the things that we can look out for to make sure that our work has more impact. So I'm really excited for that. And please, the stage is yours.
Good, thank you very much. I'm so glad that I'm here. You know, the Netherlands do a very good job at PV, are one of the world leaders of new installations per head. And also in research it has been going on really well, and I'm really happy to be here, and thank you for inviting me. Yeah, so how can research support PV fulfilling the Paris Agreement? And I first start actually with the Paris Agreement. You're probably familiar with that graph of CO2 emissions globally over the years. You know that mainly coal, oil and gas is burned. This is the main reason why we have global warming. It's also technology related, you know, the electricity generation makes a big part of it, but also transport, manufacturing. And it's good to actually think of a carbon budget instead of a path. What I show you here is different ways of having the same 420 gigatons, the area under the curve of carbon still left for official 1.5 degrees, and you can go down steeply or less steep, and if you go even slower you need to go somehow to negative emissions. And this is just a simple top-down calculations with a differential equation of population, which is often used in industry for diffusion of new technology. Yeah, so when you think of how can we come down, it is often good to look at different modeling of the energy transition globally, and they say more or less about 3/4 of CO2 needs to be replaced by PV, and the rest by wind, whatever is left. So 3/4. When we calculate that, how much PV we need to add in those 3 different curves. So the one is the very steepest curve, 4 is the slowest one with a budget. You see that you need an a big addition. This is capacity added per year. It's not the overall capacity. And the red arrow is how much you added last year globally. So you see, well, we can't go down that steeply. And you often see steep curves going down, what people expect what we should do. But when we want to do it with technology and with PV, we would need to add about 20-fold of new capacity for PV production than we have now. So this looks rather unlikely. And what looks even more unlikely is we have to go down by 35, the latest. And that also means we need to replace cars, parts of industry, etc. with electricity. Most of industry is already electric, but an important part isn't. And that makes it even less likely. So what about going to 1.6 degrees, just 1/10 of a degree higher? And if you do that, you see it all shifts to later times, and especially it lowers the necessary added industrial capacity of PV production. So this is again what we added last year globally, and this is how you need to go along those 4 just top-down curves. I mean, this is not a real prediction, it's just a kind of a model thinking I'm doing here. And when you look at the annual growth rates of PV production over the years, that's the historical points there, so we are actually here at the moment, about 40% per year. So we are actually on the path that would fit more or less the trajectory of 2. So you may ask, well, what about if we do other stuff to go down to 1.5? But see, the difference is quite big. It's actually even a little bit bigger than we had during COVID. And we would need that with better efficiency or sufficiency, which means you do less flying, whatever. We would need to do that over all these years. We need to keep doing that, not just a little dip in COVID like we had. Well, it's often said we need to be carbon neutral by 2050 to meet the 1.5 degrees target. Well, it's a contradiction. It's not possible, really. And I find 2050 has become a metaphor. That's not a number. I mean, it's a metaphor, and it's a metaphor for postponement. What I forgot to tell you, the committed stuff here, that curve, is what is committed as infrastructure that emits CO2. This could be our cars that are not paid back yet, it could be industrial facilities that are not paid back, or mining rights. And it shows to come down, we need to remove our cars before they are at the end of their lives. We need to scrap industrial facilities before they come to the end of their lives. We need to do that, otherwise we don't come down. And we need to take away even mining rights and rights to get more oil, whatever. Okay, so this is the CO2 curve of so-called integrated assessment models. That's models that models energy transition, but also global warming, etc. And this is from the IPCC 6 report. And what you see is that actually the majority of those models assume big negative emissions. Well, what does that mean? It means you need to have an industry that's about half as much as you have now emitting CO2 in energy, because binding back the carbon needs about the same amount of energy as releasing it to get from. So we need about half as much industry to do nothing, just to put more limestones or to put something in empty cavities from the oil. Well, that's not a business model. This is not a business model. It's socially constructed. And unfortunately, and I'm not happy about the IPCC, that they go on like this, and then when you look at the pledges, they exactly assume that there will be negative emissions and that we will do it. But there's no business model, and we don't have even a technology for it yet. It needs to be developed. So it's highly risky to think like that. Well, when you look at all those paths, then you realize that most of them, when you look at the temperature increase over the years, actually shoot over. And they come down to 1.5 degrees at how it is defined at the end of the century. And with that shooting over, you actually put 1/3 of the population outside the niche where we are. So this is the mean annual temperature, and this is the mean annual precipitation, so rainfall in millimeters, and this is where people live on the planet. So red means more dense. So 1/3 of it will actually go off here, and this is, for example, India. So this is what it looks like, and it looks bleak. It looks like that there is a disintegration of quite a few societies. That also means you are in a crucial time in PV, and you can make a crucial difference to climate change. Just look at that. If we can go and keep going like this, we don't need to do this, we don't need to do this, but we could actually taper off at about 400 gigawatts per year additions, and in total we would have about 2 to 3 terawatts production per year. This is how we could actually do it. Okay, so I've got 2 topics. First is just very shortly how to scale up PV to terawatts, but my main talk will then be about what you can do from lab to farm. Well, this is an example of a PV utility. It has 30 megawatts. This is in China, about 700 kilometers from Beijing. It mainly feeds Beijing. And this is from Trina, and so we looked very carefully at all the materials we needed to build that PV utility, at all the chemicals we bought. We looked at the energy in those chemicals, at the CO2 emissions in those chemicals, and we did that with an independent audit from Italy. It's a life cycle analysis audit that's independent of Trina. And what we ended up with is here's the materials, up here per electric energy, produced over 30 years. Here is just in tons. And I just want to tell you that in the solar cells, the silver for the front metal things doesn't even appear here. It's so little silver we use. But what you see is, for example, glass sheets, the steel for the racking, this is very heavy. But there is also one thing we should think of, and this is cables. This needs about 160 tons of cables going along all these rows of modules, and then the cable to the next high power station, and also the cables within the transformers. And it is actually the copper that's the most critical material in that. So it doesn't tell us much when we think of a 30 megawatt utility. I thought I'd plot it as a fraction of years of global production of each material. And what we need for a global energy transition, not just in China, just for a global one. And you see, of course, silver doesn't work. We know that silver doesn't work. We are working hard on copper replacement and aluminum replacement, the silver things, because at the last slide, you didn't see the silver here. It's actually the one that runs. It's not possible to have 30 years of silver mining in an energy transition world. Brass is not so much of a problem. Silicon needs it, but copper, because there is not that much copper actually, and copper is not distributed evenly. It's mainly in South America and some sites in Africa, and many of these sites are actually in areas that are protected. Okay, so we need to watch out for copper actually. That was a bit of a surprise for us. Well, when you look now at the CO2 emissions, it is of course the material extraction and processing, and this is mainly for silicon. For some other materials as well, but not much. And the direct emission from reducing the silicon oxide to silicon and also to cement is actually relatively small in comparison what you just do with trucks and all that. And what's grey here can actually all be reduced. I mean, we don't need diesel trucks in mines. You can do it electric. Okay, so when you look over the years of how much CO2 was emitted for fabricating a solar cell in an industrial environment. I mean, in 1990 it was a small-scale industry, and you looked at the emissions in grams per kilowatt hour. We are down now to about 15 grams per kilowatt hour. So scaling that industry up for a global energy transition, still assuming 3/4 of all CO2 is replaced by PV, scaling that up will take us about to 3 to 4% of the remaining carbon budget. Because it's an industry, it will be a huge industry, it will have an impact on our CO2 emissions. And this is just a rough estimate of assuming we go linearly down with our CO2 emissions in the mines, etc. If we don't do that, it may be more than 3% of the CO2 budget. We are very lucky because if we were just in 2000 or 1990 and we had to scale it up, we would use more than 1/4 of our remaining carbon budget to scale up. This is how important it is that people like you do research and development. Because it's only you, people like you, who have done that. This is one of the very important messages I want to give you as a motivation. It matters what you do, and you can do a difference to the planet. And just to show you a last slide of this section, this is Trina factories, and this is just different things we needed for our production. So fossil gas, electric power, water, and our CO2 emissions. The study I showed you with this 30 megawatt plant was done in 2018, and we already halved the cell. This is only cell production. We already halved the CO2 emissions of the cell production. I think it's important for the way to go to terawatts to have PV manufacturing all over the world, not just in China, especially in Europe, in the US, maybe in other countries like Near East or India is picking up. And why? I mean, when you look at the growth, this is the total production capacity in gigawatts. When you look at when was it actually going up steepest, it went going up steepest when there were many countries together to actually produce solar cells. And once China took over, it slowed down again. I mean, it's going a bit steeper again in China now, but it's important that we distribute manufacturing, and even more important, that we distribute our supply chains. Don't forget the supply chains. If you always have all materials from one supplier, this is not a resilient supply chain. Okay, so what can you do from lab to fab? Well, I heard that many of you are doing research in perovskites. You are very lucky that actually your material has a certain structure, for perovskites, and it has a high ionicity, and that means the formation energy of defects are actually very high for deep defects where you have easily shockable volume combination. So when you look at those formation energies, they're low, as long as they are fairly shallow. I mean, that can be a problem for doping, that your doping is not as stable as you want, maybe, but it's good that you need a low energy for that, and you need very high energies for those. That has given you a high VOC from the start, and that has actually been one of the main reasons why your material had a kickstart. You really had a kickstart, And this is because of that. If you had another material, like a highly covalent material, your bonds would be most likely in the middle of the lab gap, and you wouldn't have had a high VOC to start with. You would have to start very slow. This is what you actually see here. So it's important to know what is actually limiting my performance. Now the VOC is very high, perovskite cells, of course, but when you look at the past, what crystalline silicon solar cells have, First they had no passivation. It's like perovskite, you had no passivation for a while. It tapered off. And it took actually 20 years till people saw, wow, we actually should passivate our solar cells. You know, these are all world records, but the empty symbols are internal stuff. And then actually only with passivating the emitter we got higher till we tapered off at 2000 in a way, and then comes the passivating contact. You may have heard of, if you know about silicon PV, that's a kind of a contact where you don't have as much recombination, and actually it is a design you can afford with that makes the cell better, and you get a bit higher, and the Schottky twice limit will be around here. So we are getting close to the Schottky twice limit. The industry is here. And look at the kickstart you had, but here you had the same phenomenon. You had a saturation of your record efficiency. And then people in the last two didn't put the very last values a bit higher than one shift. I don't know. People did different things to it. They thought differently about that devices and knew what's limiting that devices and started to solve that problem. And that's how they didn't taper off here. So, you know, thankfully not for 20 years, but they went. Okay, so my first message is know your losses, your devices in detail. Because only then you can work on your limiting losses. Otherwise you're very likely to work on losses that don't matter as much. And for perovskites it's degradation, but we will come to degradation next. Well, when I look at some publications about what kind of materials are used in PV and in wind, you find a whole lot of different materials people think we need them for PV or for wind. And you probably know, I don't need to tell you, we don't need all these materials. You can actually do stuff with very little material. Just remember the silver. The silver didn't show up on the mass graph, but it showed up on the material production graph. And that's similar to here. Though, just read. Yeah, take it in. Take that in. Yeah. And there is one more thing, and this is economy. I mean, I'm glad you don't think of economy. It's important to have free thinking. But still, I mean, out there is economy, and you may choose some different paths on your free thinking. Still free thinking in a way, but you know, Picasso had a blue face, and he was very creative in his blue face. Well, it was a restriction to some colors. He did. Artists often do that. Why shouldn't we scientists sometimes think a bit of economy and make some restrictions of materials, whatever, to be more creative, like Picasso was in his blue face. I mean, it was a sad face for him. So I'm probably saying it should be a sad face for you. So what's shown here is the competitive relative model price after you plant a PV utility. You know, PV utilities are really under price pressure, not so much on your rooftop. You go after how it looks like, etc. as well, but in utilities, that's where the price pressure is. So you put it all together in your planning, and now you need to choose, should I choose a module that has high efficiency, that can of course cost a bit more, because I get more power, I need a bit less racks, but it must not cost too much more, otherwise I won't earn as much, or I will even spend money instead of earning. This is what this curve shows. So if the module is above that curve, it's not competitive. It's below, of course, it's competitive, and everyone jumps it. So this is how the different cell types you have these days are aligned to that very narrow range. And this is actually top coming down to that curve. And that's one of the reasons why we have a technology cycle from purple to top. Those are still far too high. So it tells you, in a way, that in earlier times, amorphous thin film cells went down the cliff. So imagine you have an amorphous cell that has 12% efficiency. You would need to pay some utilities that they will take it off, because you are here at a negative. You know what I mean? And also it means for your tandem people, when you do silicon perovskite tandems, even if you are quite high, and this is module efficiency down here, you know, it's not cell efficiency, much lower than cell efficiency, you actually cannot be really much more expensive. It flattens down. And of course it depends a bit on the country, how flat it is, it depends how expensive the land is, etc. But just give you a rough idea. So this economical pressure, just read. And I think this would be something you can think like Picasso. When you have something that really doesn't fit that at all, it may be better to spend your time and intelligence and creativity on something else. That's just a suggestion. I don't tell you what to do, but it's something you can reflect quietly in the evening when you go home. Does it actually fit more or less something like this? Does it have a chance to be applied? Okay, so you have no real losses, you have no scarce materials, you have sufficiently high efficiency versus cost. With perovskite, it may be mainly the cost thing. And we also need stable materials. So when I look at the literature, I mean, I'm not doing perovskites myself, I just look at the literature because it interests me and I really hope for perovskites. I don't see an alternative to perovskites at this stage. I see a plot like this. Look, this doesn't mean anything to someone in industry. If you just have 1,000 hours and you plot it from 0 to 1 on the curve like this, it doesn't tell you. So how is it possible that really good journals like Nature Photonics, etc., allow people to actually depict in such a graph? It's not something useful for industry. It doesn't give confidence. Also, the active area. I mean, look how tiny it is. In industry, I wouldn't rely on any measurement that's an area smaller than a square centimeter. That's about where the lower limit is. Why? Because many things can happen at the edges. You may get electrons in from the edges if it's small. You don't know where your device really is when it's so small, do you? And then also, for example, they were scanning at a very high rate. And I think, well, you got metastable defects. Did they really always put the metastable defects at the same state before they measured, etc., etc.? So this doesn't really convince me when it's communicated like that. And it doesn't convince me when the title says stable something. It has become a bit fashion to call it stable in the title. And when I read the papers, I see, well, but they didn't really look at stability as such, or didn't really do research on stability. So there are no validated, really, ways to really test stability. That should be done urgently. And I think you should do extended outdoor tests of many samples. You don't need an MPP truck. You can just use a resistor, so it is more or less an MPP. And then take it off every week or two and measure it in your lab, put it up in the roof again. And do that with many small samples. So you really have an idea of, we change this and that sample, and it is more stable than the other, for example. And for a later stage of industry, the binning methods, I mean, you need to measure IV curves and decide which cells you put in a module. That's very important, often forgotten. Otherwise you have a so-called mismatch. It's a module and the efficiency goes down quite a lot, so you know the mismatch. Okay, but what makes me really hopeful that you will get stability is, look here, is the number of publications per year over 3 years in different fields of PV. And the perovskite has about 2,500 papers per year. So it's a huge community, and actually that went further up than the dye-sensitized went down, and that means people from other fields came into perovskite. And that's very valuable. That's very valuable because, you know, we know that defects don't lower your VOC, but they make your device unstable. And you need to passivate those defects. Well, the amorphous silicon people had no option to actually passivate the Stern-Wronski defect. And so they couldn't solve that except for high doping. But you've got many, many possibilities to actually stabilize it. But that also means you're likely that not just one ingredient will stabilize it, or you may need many ingredients at the same time to stabilize it, just from likeliness. Okay, so the next thing is simple fabrication and high yield, because if you got different processes and you got a certain yield, and say the yield is always 95% after 8 processes, you can throw out a third of it. So be aware of yield is very important finally for putting out in the field, for instance. The 6th is, as I said, a free mind, but yet be strategic. And strategic, I mean, it's okay when labs use spiro, if they use gold electrodes, if they use spin coating, also this is not an industrial suitable process, spin coating. If they have, well, that's a bit small, but it's all right to have small areas to be quick, you know. That's all right for your base process. I mean, you need a base process that's stable, and then you do something new to it, that you can see the difference. If your base process isn't stable, you can't know whether something improved or not. And that's why this is all right for a stable process you need to see things. But it's not all right if your whole lab just clings on that and doesn't think of, hey, will it actually work with something more applicable? Then you're very likely that it won't be used in industry. Okay, and finally, just to finish off, time is over, watch the moving target. The moving target is what's out there. This is crystalline silicon TOPCon cells, PERC cells. And, you know, fabrication gets quicker and quicker. This is throughput of a single 2 pieces per hour. It gets quicker and quicker. Things are faster and faster. That's one of the reasons why it's cheaper and cheaper. There is a community that's, on one hand, competing with each other, but it has a moving workforce. I mean, these people go from one factory to the next, they bring the knowledge to the next, etc. So there's lots of gossip in the silicon PV community. I know from former employees what they are doing, etc. There is, and this is most important, there is a single fab technology. Every business uses the same tools. And that's what makes progress so quick, because you can absorb knowledge from other companies because you have the same tools. Yeah? And as I said, supply chain, wafer sizes, all tailored to that single fab technology, and that also gives trust of investors. This is the moving target, and this is what you have to fit in eventually to be successful with growth. And that's how actually, the different cell types have those technology cycles from standard to PERC. Now it's happening to TOPCon. We don't know whether heterojunction comes or not. That's a big question mark. And also when tandems come, we don't know. That's the future. We really don't know. I can't tell you. Nobody can tell you, I guess. And this is what makes you so important to be here. And with that, I thank you.
I'm sure there are questions. We have about 5 minutes, something like that. Questions?
Yes, thank you very much for this interesting presentation. I have a question about this graph you show here in your slide.
Yeah.
It seems that there is no more industry after 2040. So can you comment on that? Did you account for the replacement of the first generation of PV modules that needs to happen maybe after that time?
Yeah, as I told you, it's not really a prediction, it's a thought experiment with just a differential equation. And don't think too much of what's happening here. This is actually the additions, the manufacturing additions. So of course the PV industry keeps existing, but it doesn't need to add as much anymore in total volume. And when you go to negative emissions, of course you need to keep going with additions. I mean, you saw those curves from the IPCC 6, for example. So it's a good question what you say. I would say don't trust that. The model is not done for that stage. The model is done to show you the rough additions you need over time.
Yeah, but in this curve, has the finite lifetime of PV modules, that is say about 20 years in this graph model?
Yeah. Yeah, of course. I mean, at the moment, the warranty lifetime is at least 25 years. It's usually for PV utility 30 years. Well, you don't throw out your fridge when the warranty runs out. It's the same with the PV modules. I mean, that's when it's incredibly cheap to produce power, is when it's all paid off. And they still have 85% of the efficiency after end of warranty. Why should you throw it out? What you will replace is, of course, inverters. You may also replace something else. And they are, after between 30 and 40 years, more and more modules will degrade, and you will replace them. So there will be a partial repowering happening. That's what's economically most likely. And if you count that in, I mean, as I say, this is a rough model for just estimating stuff, but you actually don't need to expand PV for replacements, because this is a constant thing happening. You don't see it in that graph.
I guess the question is about where you put the steady state. Right?
The steady state is about 2 to 3 terawatts. 2 to 3 terawatts of production is the steady state in that curve. You know, if you go that one, you came down with the CO2 emissions, and when you look at the end of how much production capacity absolute do you have, I can show you. It's from China. I have it somewhere. Batteries. No, I can't find it, sorry. It's about 2 to 3 terawatts where we level off, but if you go the bad way, if you go to curve 4, it's about 7 terawatts. So that one, if you do that, you end up at a constant production rate of 7 terawatts per year.
Doesn't that put the problem of the business model going for the companies because they have to then grow up quite a lot, and then
No.
no company wants to do it?
No, it's the contrary. At the moment, investors don't earn money. It's growing too quick. And that's normal for a young industry. It was normal also when they did fracking in the US for LNG. People didn't earn money. In contrary, many companies went bust in the US. They only earn money now in the US with LNG because they don't expand anymore. And actually LNG is coming soon to an end in the US because they don't invest anymore. They want to earn at some stage some money. And the same is with PV, the investors we got at Trina, they don't expect a return in the next 10 years. But after that, then they want return. And this is when the return starts. That's when you start to earn money. So this is the business case you have, and not this. This is actually just gaining market share. You invest because you hope in 10 years you will have such a high market share that you will earn money. And what we see now is not earning, it's a fight for market share. This is what's economically happening.
Fascinating. Let's move on. Albert.
Yeah, this was super fascinating. Thanks very much.
Thank you.
I had a question about the goal shift, or how the companies connect.
Yeah.
We know in the semiconductor industry, the computer chip industry, there's a lot of collaboration, also because there's a roadmap, there's more Schall.
Yeah.
But more the roadmap, it means that the companies have some kind of agreement with each other, what they're going to do next year and so on. Then they adjust their machines. I guess in the PV, that kind of roadmap is also the supply chain, which is a crucial thing that also connects all these. So if you're saying, say in Europe, we need to build a more PV industry, we need to have a whole supply chain. But how do you organize that? I mean, the semiconductor industry, they just sit together every year to make their plans together. But how do we do this in the PV industry, that we make sure somebody makes the silicon, somebody makes the wafers at the right scale, and so on?
Yeah, so in China this is done collaboratively. I mean, the owners of the different factories, they come together very regularly. In our canteen we see also people from the factories very regularly. That works well. The Germans aren't good at that. When the German industry went downhill 2012-13, they started talking to each other at the very last minute. And before that, they were just competitive. So it could be a bit of a mentality thing, maybe, yes. And in Europe, it's often said we need a European supply chain. I would say this is quite hard to do. I mean, why not having an international supply chain, a diverse supply chain that gives you a kind of stability instead of hoping everything from Europe, for example. It also gives us a chance to actually export human rights, to export good working conditions, etc., with actually having deals that are more just than we do now. I mean, Europe has really a bad record in making contracts with third world countries, etc., and breaking such contracts. So we could actually also improve that when we think of a PV supply chain. And why should aluminum be dug out from Nigeria, shipped to Iceland? Nigeria gets so much benefit money-wise, Iceland gets so much, and then the aluminum comes to Europe, we get so much benefit from it. This makes Nigeria poor relative to us, and we do that with many things. We do that with our shirts and whatever. Yeah. And this is the problem we have, I think, and it's not up to whether the supply chain is pure European or not. So yes, I showed you in the material graphs of how much materials we need. For silicon PV, it didn't include perovskite because that's mainly chemical. And well, mainly it has some other materials that can be crucial, of course. And that's why, yeah, it will take years.
Yeah, thanks.
Yes.
I mean, China will lose a job. Even if we are very fast with our I mean, I'm involved in setting up factories here in Europe because I got the knowledge from China. I'm happy to do that. Even if we do that and we get 30 gigawatts per year by 2025, what the EU Commission actually ordered us to do, it will still be the main job of China to do the energy transition. We are too slow, we think too small. So. Does that answer your question?
Good to think about how to think bigger. Arthur.
I'd like to finally remark about Europe thinking too small. 30 gigawatts would be more than 100, at least my opinion, to have a fair share. Another thing is, of course, to create that, you need to my opinion, it's important to have a level playing field.
To have?
A level playing field, so over the whole value chain. And at the moment, you can see all kinds of initiatives in the US and India, and now, of course, China already has it for many, many years. How do you see that to create, let's say, a fair share all over the world for the whole value chain, and also creating a level playing field with respect to cost and so on and so on?
So you mean that, say, cheap Chinese models can undermine our local business? That's what you
direct or indirect
say?
subsidies.
Yeah, well, I think the COP, like the COP28 that's coming up in Doha, that's not a working mechanism. Because when China spends, say, $100 for CO2 mitigation, it only profits $30 and $60 or $70 are actually benefited by all the other countries. It's the same with the US. They are not interested in putting in dollars when others in total get more benefits than themselves. That's a system that doesn't work. So I think what could work is what William Nordhaus, as a Nobel Prize laureate for economy, suggests, and that's what your maybe the answer to the question. He suggests we should found clubs. A club has certain rules. The rule will be a timetable for CO2 price, whether you do it with a tax or with trade, doesn't matter, it's just a price of CO2 for the future. And whoever joins that club must adhere to that price and can add some customs to anything that's important. That's imported from other countries that are not in the club. So you don't need to go and see, oh, how much CO2 is in a toy for children, say. You just say, on all imports, we have a certain percentage of import tax from countries that are not in the club. Guess how much percent of duty do you need to ask at the border? That it actually is, in a way, tempting for other countries to join that club. Yeah, it's a few percent, 3, 4, 5%, no more. So we could do the same if it's not done for the whole industry and for all import goods. We could at least do it in PV. So we say, well, in PV we actually set up clubs, PV clubs for certain countries, and they do the same just with modules, with racks, with inverters.
This is fascinating, and I think a perfect place to stop this session. Let's thank Pietro again.
Thank you. Thank you. You don't have one.
Okay, so it's my great pleasure to introduce the next speaker, Ivana Milic. And actually, it's your first time at AMOLF. Really happy that you're here. But your devices have been here for a long time already. So we're collaborating for many years now, and they've been tested over there in the lab. And so very happy that you finally also made it in person, not just in device form or online form. So Ivana is leading the Smart Energy Materials Group at the AMOLF Mercury Institute in Freiburg, in Switzerland. Beautiful place for the chance. It's a very nice institute, a bit like AMOLF in terms of size and focus. Yeah, she's very successful and really one of the up-and-coming future leaders. Also has been awarded the Future Leader Prize from the ACS Society, and many other prizes. I will not read them out. Maybe just a few. Helvetica Prize, Green Talent Award. She's part of the Swiss Young Academy, the Global Young Academy. So really, clearly one of the up-and-coming future leaders in the field. And if you look at the field, it's perovskite.